Okay, so for the first question, they asked to describe the appropriate metrics for the external standards and for the blank. So since nitric acid was used to prepare the sample, it should be used as the metrics as well for the external standard and blank in order to reduce the spectral interference. So usually nitric acid is more preferred as it's compatible with instrumental methods. It is safe and also it's easy to purify it. Nitric acid is added in excess so that the contribution of the naturally occurring interferon is insignificant. And nitric acid is also chosen because all nitrate salts are soluble. And the method that is used to carry out this experiment is standard addition method.
Okay.
Should I move on to the second question, Doctor?
Yes. Unless we have a question from your friends.
Does anyone have any questions?
Yeah. Let me go on for the second question. So, what is the background correlation necessary for the analysis of zinc, but not for the analysis of copper? So the wavelength used for copper is 3 to 4.8 nanometer, while the wavelength used for zinc is at 213.9 nanometer, which is lower than 300, both also lower than 300. When the wavelength is lower than 300, the interference from the sample is high, which contributes to the background absorption and scattering. So these are D2 lamps used in background correction, as it has continuous source and the absorption of radiation by analytes. Narrow absorption line is negligible. So the resulting absorption and scattering constitutes the sample's background and may present a significant problem, particularly at wavelength below 300 nanometer, where the scattering of radiation becomes more important. Shorter wavelength and high frequency scatter more due to the waviness of the line and its intersection with the particle. The waver the line, the more the chance it intersects with the particles.
Okay, continue please.
Okay, and for the third question, a copper hollow cathode lamp has several emission lines. So explain why this method is used as 3 to 4.8 nanometer. So the value of P naught at 3 to 4.8 nanometer is the highest, which actually indicates that there's less uncertainty in the measured absorbance as the line is most intense. So in the concentration, as can be seen from a table, when it is 1.5 milligram copper, it gives an absorbance of 0.20, which shows that it has the highest sensitivity compared to other wavelength. And also, a wide monochromated slit improves throughput of radiation and narrow enough to eliminate stray radiation. Usually, the wavelength that provides the best sensitivity is the one that we choose. So P naught is also known as a source of radiation entering the sample, and the value of 100 means that it has high sensitivity.
So thank you, room 1. So please, also, you have the fourth question is for the other group, right?
Yes, Doctor. Yeah.
You can please share the answer in our WhatsApp group later. All right.
Okay, perfect.
All right. So, okay, can we have the room 2 quickly? Room 2? Room 2, do you have any difficulty? Are you okay?
Okay.
Okay.
Okay, can you see my
Yes.
slide? Okay, we are from group 2 and me, Idayu, Aina, Hanzel, and together with Omar. For the question 4, a bovine liver standard reference material was used to evaluate the method's accuracy after drying and extracting the sample. An 11.23 milligram fat tissue disease, deposit tissue, sample give an absorbance of 0.023. Report the amount of copper in the sample in microgram per gram of FFDT. From the calibration, so we plot the calibration curve from the data. We got the linear equation with y equals to 0.0661x minus 0.002. And we want to find the amount of copper in the sample. So we use the equation here to calculate the concentration of copper in the sample using the absorbance value and equation calibration curve as below. So we find the X is 0.351 microgram per ml, the concentration of copper. Since the sample was dissolved in a volume of 5 ml, the final volume in the volumetric flask, we need to convert the concentration to microgram as follow. So the amount of copper equal to concentration of copper times volume of sample divided by mass of sample. The amount of copper is 0.35 times 5 ml divided by 0.01123 gram. So we get the final is 156.28 microgram copper per gram FFDT. This is the amount of the copper in the sample.
Yes, correct. So thank you, room 2. Please share the answer with our group later. All right.
Okay, thank you.
Room 3.
Prof, hello, Assalamualaikum. Prof, actually, my group have mistakenly discussed the other question. The Idayus just presented just now.
Okay, I can share my answer. Okay. Everyone can look at my screen.
Yeah, we can see your screen.
Yeah. Question 5. Mercury was describe possible protocols in analyzing mercury sample in oil and gas sample. My answer is mercury was extracted from samples by emulsion include EIEB, and the mercury in the extract was analyzed by cold atomic. A solution mercury using a laboratory's made gas mercury was quantified. I searched from a easy. This matter.
Okay, it's okay. So one thing is we have to think about the sample. The nature of the sample is oil and gas. Okay? So usually from oil and gas industry, the sample is it might be wastewater, it might be condensate, so it might be in a bit of liquid gas. Yeah. So we have to think about it. And why we are using full vapor AAS? Because of the volatility of the organic mercury. Yeah. So this is a real issue in Malaysia. So that's why I brought up this issue to analyze mercury in oil and gas industry. It's okay. Your group misunderstood. So I was hoping to get how do you prepare the sample, right? I mean, you have some ideas, and why do we need full vapor EAS? Yeah? Since this is a real, we can get from resources from journals. It's okay. This is the first practice. So thank you, group room. No, it's room 3, right? So can we have the last room, room 4?
I'll share the file first.
Yeah, sure.
Can everyone see the file?
Yeah, we can see your screen, but can you make it larger? Now it's 100%. Probably you can make it 120. Okay, right, correct. Now you reduce back to. Okay. Make
Is
it.
this good enough?
Yeah, I can see.
This is a closer angle without going too much.
Yeah.
Wait.
We
So
can.
this, so our group just discussed the disadvantage of flame atomizer. So there are many disadvantages. First off is atoms only spend a brief amount of time, about 10 to the power of -4 seconds in the optical path. So for certain elements, the atomization efficiency, which is what percentage of elements end up at ground state atoms suitable for absorption of energy, is higher if you use furnace than you use flame because of the issue above. Second, the presence of matrix effect is highly susceptible, which is effect that can enhance or diminish the response in using the atomic method. In using flame atomizer, the sample you use to do atomization needs to be larger than any other method used for atomization because you are burning it. So yeah, basically in compared to the other types of method in general. The fourth disadvantage is that it causes chemical interference due to the formation of compounds that cannot be burned within the flame. This result is usually very low on the spectrum, but still chemical interference, especially for certain substances like listed here are polyvalent cation in the presence of polyvalent oxyion or fluoride containing substance. And fifth is narrow range of linear response. And the next one is only solutions can be atomized by the flame, which is another disadvantage. Ionization interference caused by the formation of ions within the flame. Lack of recognition and control of this problem can produce either positive or negative error during analysis. This effect is usually responsible for anomalous curvature within the calibration curve. Example for all the alkaline metals show this interference in the acetyl air flame. Most elements show this interference in the acetyl nitrous oxide flame. And the next disadvantage is that it's not as sensitive as graphite furnace, especially when the sample size is small. And refractory elements might have issue being atomized using the flame. Refractory elements are elements that are much more resistant to heat or high temperature, since they resist heat, so it's much harder to atomize them. And lastly, the last disadvantage is background absorption or scatter caused by molecular absorption at resonance wavelength, or light scatter due to very small unvolatile particles inside the flame. This phenomenon is wavelength dependent, very great at short wavelength, but will always give positive error during analysis. And that's all.
All right. Thank you, everybody. I think you have done a good job. Okay. So in short time, you managed to answer. Of course, all the answers are easy to Google. All right. If you are like instructed by your company to evaluate which brand of AAS, which brand of AES, then at least you have some idea now how to evaluate. You can talk to the provider. Okay. When he or she, the supplier talks about technical jargons, at least we can understand, okay, in terms of sensitivity, in terms of any issues of interference, what kind of innovation they have, okay. So at least we have some ideas on how to select the best system for your AAS or for your AES. Yeah. So as I mentioned, if you have money, please do buy ICP AES because it is more robust, multi-elemental analysis. If you have just small amount of money, AAS is fine, but a lot of work has to be done. You have to buy multiple light source, depending on your element of interest. Okay, so next week, I will stop recording.